Thank you. So first, I want to thank Antoine and Quanton for organizing this school and for the opportunity to be here. I guess just kind of my personal view is the last few months have shown that, for the most part, it's possible to do science during a pandemic, but it's really not the same without, face-to-face interactions. So especially, thanks for trying to bring back some aspect of that here, and also thanks to all of you. And for also trying to create, the safest possible environment to do that. So I'd like to start with just a bit of an extended introduction about why it might be interesting and useful to create quantum interfaces between atoms and light, and also about the standard theories that we have to describe these systems, to predict how technologies might work, and so on. So this is meant to be a little bit more of a kind of big picture overview level. I certainly can't do the theory justice in 15 or 20 minutes. So the goal isn't really to, for you to remember all the details of the equations. Although if you have questions, feel free to ask anytime. The point is more, again, more to introduce the main ideas. And actually the main message, I guess, of these lectures overall is maybe in the end we shouldn't be so happy about what we learned in the textbooks anyway. Okay. So let's just start with a single atom and how it talks to light. So a single atom, is a pretty simple system. We all learn it in quantum mechanics. But it's actually, at the same time, a remarkable optical device. So, when I say atom, I'll take some minimal model. So any atom, for example, hydrogen will have some electronic ground state, a first excited state, and so on. That's kind of labeled here on some vertical axis that denotes energy. I'll just denote these two levels, G and E. And of course, the way that you can go from the ground state to excited state is by, shining in light, a laser, for example. That's resonant with the atomic transition. Of course, an atom has higher electronic levels as well, but because of this because of the Coulomb potential, the energy spacings are very anharmonic. So what that means in practice is if you come in with a laser that's near resonance with this G to E transition, there's not really any more transitions that you can readily excite. So because of that, that means that this, this single atom can fundamentally really only absorb and emit single photons at a time. And the single quantized photon is already interesting because it's a non-classical state of light. It has properties that you can't completely explain or understand from classical principles alone. And of course, one of the kind of big interest in generating non-classical states of light these days is for quantum information processing. So atoms and light have many other possible applications as well. So one of them is, for example, to realize interactions of light with itself, the nonlinear optics, really at the level of single photons. So single photons really notice each other's presence and have effects on one another. You can imagine using that to create, switches and transistors that operate on the optical switches and optical transistors that operate at the level of single photons. Or if you're interested in quantum computing, to maybe realize quantum gates between individual photons. So, kind of heuristically, the way that might work is, again, a two-level atom is quite special. So it can, in principle, respond to single photons. So you might create some kind of device where a single photon comes in, interacts with the atom, and then that photon will be reflected into some channel. But again, because a single atom is a two-level system, if you send two photons at the same time, the atom doesn't really know what to do anymore. So it's really more likely that these two photons will transmit. Okay, so it's reflecting for one and transmitting for more. That's a very, that's an example of something like an optical switch. You can also imagine building quantum memories for light. So again, if the idea is to build quantum networks or quantum computers, it's easiest to transmit quantum information over long distances in the form of photons. So you can, for example, encode quantum bits in maybe the polarization degree of freedom of light. But it's not so nice, if you want to kind of keep information in one place for an extended time, just because photons fly everywhere and they do so very fast. So you know that in quantum mechanics you can't just directly measure the photon without disturbing the wave function. So you would really like some kind of coherent map, to just kind of store the wave function without you knowing what the details of that wave function are. And so a quantum memory of light basically involves sending in a photon, and through some kind of unitary or coherent transformation, mapping that wave function onto some wave function of an atomic system. And hopefully that's kind of reversible and on demand, so when you want to retrieve the information, you can do so at your desire. Atomic systems can also be used for metrology and sensing. Just as an example, atomic systems are naturally respond to certain external stimuli. For example, a magnetic field. So magnetic fields, for example, can wiggle the energy levels of an atom around. And now if you send in light, the light might be sensitive to that change in the atom. So it might, for example, change the phase of the light going through, or its polarization. And then finally, if you can measure the light, you can go back and try to extrapolate what that magnetic field was. So here I kind of illustrated it for a single atom. You can also imagine doing it with a collection of atoms. And then you can maybe also imagine using quantum correlations, like entangled states, to improve how sensitive the system is. And it turns out to generate this entangled state, one natural way to do that in the first place is also with light. So these are a few of the many examples of why people are interested in building quantum interfaces between light and atoms. So if that kind of hopefully piques your interest, the next thing that is kind of natural to ask is, how do we develop protocols for the applications or phenomena that we're interested in? What's the kind of underlying theory that we can use to predict, for example, how well these protocols will work in real life? So when I say develop a theory, maybe let's just start by thinking about the actual complexity of this quantum problem of atoms interacting with light. So if I want to develop a full microscopic quantum theory that includes all the degrees of freedom, well, so in these lectures, I'll primarily be interested in ensembles, collections of atoms. So a cold atomic gas can easily have something like 10,000 atoms or more. And if you just take this minimal model of atoms interacting with light, so an atom is a two-level system, then the dimensionality of that Hilbert space comes out to 2 to the 10,000. Okay? So that's way more than all the atoms in the entire observable universe. Moreover, you also have the atomic positions. In a gas, you don't really know where the atoms are, and they're moving around all the time anyway. So that's just the atoms. And then when you include the light, well, the light is actually a continuum of modes. So light can have any frequency. It can go in any direction. And for each one of those modes, there can be any number of photons. So that's an infinite Hilbert space. So you see that you're basically kind of stacking infinities on top of infinities. And it's really not a kind of recommendable approach to building a kind of a tractable theory. Okay, so I wouldn't recommend it. So to try and have some predictive power or to have some kind of tractability to the problem, the standard approach, which you can read in more detail in textbooks, is to develop a macroscopic quantum theory. Okay. So in particular, most of the time when we talk about atom-light interfaces, we'll be interested in cases where you have a collection of atoms, but the light that you send in is in a well-defined kind of quasi-one-dimensional mode. And furthermore, you collect light back into that same mode. So an example could be something like a focused Gaussian beam. So given this kind of quasi-one-dimensional nature, the macroscopic equations, well, first there's a kind of Maxwell equation. So we write down a kind of one-dimensional wave equation for just this kind of set of modes of interest. And then the atomic polarization, which in this case is just the atomic coherence between the ground and excited states. That serves as a source for your field. So if this equation was classical, I think all of you would be at least somewhat familiar with it. Now it turns out in the quantum domain, basically both classical fields and quantum fields obey Maxwell's equations. So the equation itself doesn't change. You just put operator hats on the electric field and on the polarization density. Next, if you just write down the equation for the polarization density, well, strictly speaking, it's a product. It's a sum of a product of delta functions and positions that corresponds to just the density of atoms, taking into account the specific positions, times the atomic coherence between the ground and excited states. So just to establish some notation, if you're not familiar with this operator sigma GE is just a short form for this operator here. So if sigma GE acting on atom J takes atom J if it's in an excited state and lowers it to the ground state. So this equation for the atomic polarization density is formally exact. As I mentioned, though, in a gas, the atoms are moving around, and you don't really want to keep track of all that motion. So typically, what's done is a kind of smoothing approximation. You say, I don't really care about the granularity of atoms anymore. I can just treat it as some smooth density times now what looks like a smoothed out polarization. So a classical analogy is a little bit like a kind of like a prism. When you ask someone how a prism works, or if you ask me how a prism works, hopefully I don't tell you about the 10 to the 23rd eigenvalues that a system has. Instead, I try to describe it in terms of more simple parameters, like a macroscopic refractive index. Finally, we have to write down an equation for the atomic polarization. So just as the polarization acts as a source for the electric field will go and drive the polarization. It'll induce some dipole moments in the atoms. So this kind of block-like equation is exactly the same that you would have for a single two-level atom interacting with the field. In particular, the time derivative of the polarization is given by the product of the electric field that the atom sees times the atomic population inversion. There's one more term here, which is important. So remember here that the electric field is not the full three-dimensional electric field. It's really just this kind of electric field in this kind of one-dimensional mode of interest. But at the same time, the atoms still see all the remaining continuum of field modes in 4 pi. And for a single excited atom, we know what these continuum of field modes do. If you have an excited atom, it'll just simply spontaneously emit a photon into 4 pi at a well-defined rate, gamma naught. Okay, so this kind of dissipation of the atomic coherence just really represents the emission into the remainder of 4 pi. So that kind of illustrated that here. So these equations together are what are commonly known as the 1D Maxwell block equations. They really are standard model in a kind of practical sense of quantum atom light interfaces. I should say that maybe these equations look simple, but they're still not easy to solve in general, especially once you account for the fact that these are all operators. Okay, so abstractly, this is some kind of quantum field theory, one-dimensional quantum field theory that you're trying to solve the dynamics of, so something out of equilibrium. So to make progress in general, you usually have to make further approximations to this model. Okay, so again, the goal is not to go into these equations in a lot of detail, but I do want to mention a couple of important points or physics that these equations encode. So one is the idea of collective enhancement of atom-light interactions. And to motivate that, let me just start with discussing the coupling efficiency of just a single atom to a single resonant photon that's propagating in this mode. So one way you can define efficiency is in terms of scattering probability. So imagine I have a single atom. I focus a laser beam, a resonant laser beam, down to some area A that overlaps with the atom. And I can ask what's the probability that a single incident photon will interact with the atom and scatter that photon into another direction. So it turns out that this answer is pretty simple. You can just ascribe to the atom some effective scattering cross-sectional area. And one interesting fact about a resonant atom is that scattering cross-section doesn't depend on any microscopic details of the atom, but it's actually just given by the resonant wavelength of the transition squared. Okay? There's another way that you can talk about coupling efficiency, which is in terms of photon collection. So if I don't send in light, but instead I just kind of excite the atom in the first place and let it spontaneously emit one photon, I know that its overall emission rate will be gamma naught, but then you can ask what's the probability or what's the kind of fractional rate that photon will go into this mode that you want, for example, this Gaussian beam that you can collect over the remainder of 4 pi. And it turns out by reciprocity that these two processes are directly connected. So this collection efficiency is also going to be lambda squared over A. And you can just rewrite that if you want in terms of this kind of branching ratio. Okay, so there's this rate gamma 1d that you emit a photon into the good direction over gamma naught, which is just the everything else. So one important point is this is an exact result. It's independent of the Maxwell block approximations. But in terms of if your goal is to build quantum technologies, you really want a 100% efficient atom-light interaction. And if you actually try this experiment, which some people do, one difficulty you run into is the diffraction limit. So it's actually hard to focus light down to lambda squared. So if you account for the diffraction limit and also some other technicalities, the record of this kind of interaction probability between single atoms and photons is about 10%. So it's not bad, but again, for technology, you want 100%. So that's what really motivates atomic ensembles, trying to use atom number to your advantage. So in this case, where I have an optical mode like this Gaussian beam that interacts with all the atoms, this optical mode naturally couples to collective excitations. So for example, single excitation states that this field naturally excites are of this form. So some atom J is excited, and with some local phase e to the ikz, that's set by the laser wave vector. Okay. So it turns out that this atom number enhances the coupling efficiency to the mode. So basically, because of the atom number, instead of just this collective mode will not emit at a rate gamma 1d into the desired direction. It'll emit at a rate that's n times that. On the other hand, the emission into free space is still largely independent. So the gamma naught, so this single collective excitation, still only emits into the remainder of 4 pi at the rate that a single isolated atom would. And that's important because again, from the standpoint of building an efficient interface, you really care about this branching ratio. The amount you collect versus the amount that you lose, so n gamma 1d over gamma naught, kind of sets the fidelity with which you can collect quantum information versus the probability that you'll lose quantum information in the form of photons into uncollectible directions. Okay, so this product n gamma 1d over gamma naught is just the same as n times this kind of interaction probability of a single atom. And in atomic physics language, this quantity is also very commonly known as the optical depth of your atomic ensemble. Okay? So this optical depth is very important. And because this is basically kind of, you can think of it as kind of a branching ratio of information, anytime you try to carry out some application with atoms and light, the errors for that application naturally should not scale any better than 1 over d. Okay? So that's kind of a quick summary of the textbook formulas or equations for atoms and light. Again, I think most people accept that this optical depth sets a fundamental limit to the efficiency of applications involving atom-light interfaces. You can find hundreds of papers that say something along those lines. So here's a review from of just kind of general applications of light and atomic ensembles. And somewhere in the introduction, it says, the requirement that the optical depth be much bigger than 1 is the most significant requirement for basically everything you want to do. Just to give a little bit more specific example of that, you can go back to this application I mentioned earlier, which is a quantum memory for light or photon storage. So you can imagine in the lab, there might be very different protocols, specific protocols you can implement to realize a quantum memory. One nice thing about this theory paper is, they kind of analyze all these approaches from a more general perspective. And they said that, all these approaches, if you optimize them correctly to your specific system, it should yield the identical maximum efficiency, which is only dependent on the optical depth of the medium. So that's a kind of interesting, broader statement. So in particular, they use the Maxwell block equations to derive the following error. So when you have a large optical depth, the error should scale something like 5.8 divided by the optical depth. So error here means you have a photon qubit, you try to store it, but then you fail with this probability. So let's kind of get a sense of what that looks like in state-of-the-art experiments. So here's an experiment for a single photon quantum memory from the Laurent group in Paris. So what they're plotting here is the experimentally measured memory efficiency, or 1 minus the error, as a function of the optical depth. So experiment is this kind of red dots here. So it's just one particular experiment, but I think it highlights a pretty general trend with many applications. So in particular, the fundamental error shrinks too slowly as a function of optical depth. So you get up to an optical depth of 200, the error is still something like 40%. And then you can try to increase the optical depth even more, but then you start to see that this error actually gets even worse. And that's just because this kind of scaling of optical depth is really just some fundamental limit. You take some idealized 2 or 3 level atoms. But in practice, when you have a huge optical depth, you start to create other problems as well. Okay, so in summary, I think a rather general problem or limitation of atom-light interfaces is you can certainly go and see interesting stuff. It's just not as robust as you want to be, and it's hard to make it more robust. So given that, I think many people are interested in finding a new way forward. I think you'll hear many possibilities of what that new way forward might be this week. And in my lectures, I just want to give my personal perspective on what one possible way forward could be. Okay, so that kind of concludes the general motivation or introduction. Again, I want to just reemphasize that if you have any questions, feel free to ask anytime. But since we're kind of naturally at this stopping point, does anyone have questions now? Okay. So actually, a few years ago, we got curious about when everyone, or I especially, learned that optical depth is the full story and there's nothing else. Is that really the full story? So if we think about more abstractly, when we say that the interaction efficiency or probability scales directly with atom number, and that sounds quite natural, but there is an assumption that goes in there. You're kind of assuming implicitly that atoms interact with light independently. So you have some notion implicitly that a photon is a little bit like a tennis ball. It comes into this kind of gas of atoms. It has a chance to hit the first atom. If it misses, it has a chance to hit the second atom, and then the third atom, and so on. So the probability that something happens is simply multiplicative in a number of atoms. But that can't really be true because the phenomenon of light scattering is a wave phenomenon. So in principle, you can have multiple scattering of light and complex interference. So different paths can add up as a coherent sum. And if we don't talk about atomic physics for a moment, but just go back to kind of classical optics, it's pretty well known there in certain circumstances that if I have just a dense collection of classical point-like scatters, when I take laser light and send it through, if I monitor the far field intensity, I get this very complex speckle pattern. That's really due to all the kind of complex interference that light can take as it goes through the system. So it's hard to kind of reconcile these two pictures with each other. Furthermore, you can kind of imagine, I'll say a little bit more about, more detail about how you actually calculate this later on. But you can also imagine or believe that this speckle pattern is highly dependent on the atomic or even just the classical particle positions. Okay, so if I scramble the positions and I redo the calculation, I'll get a completely different pattern. So how is that physics lost in the Maxwell block equations? Well, if you believe that this kind of speckle pattern depends on the atomic positions, recall in the Maxwell block equations, we kind of smooth out the granularity. So we just say the atoms are some smooth density. And so at that point, you've already lost the possibility in principle to talk about speckle and all the kind of complex interference that comes with atomic granularity. There's actually a second issue, though, which is a little bit more subtle. So, which is when we say that if we have an excited atom or some atomic polarization, it simply emits into 4 pi at a fixed spontaneous emission rate gamma naught. So this gamma naught is the same emission rate that you would have just for a single isolated atom in empty space. The issue with that is, in this kind of classical picture here, it's quite intuitive that this kind of far field intensity pattern depends on interference between atoms, right? Light can come from many different points, and then you have to add up those amplitudes coherently to finally calculate the intensity at this point. So by conservation of energy, because the intensity at any given point comes from a sum of all the atoms, if you look at the effect on the atoms themselves, in other words, the dissipation or the emission, this emission from atoms fundamentally must be non-local and correlated. Okay, so again, it can't just be an independent sum of dissipation at individual locations. Okay, so it's this kind of independent emission assumption that throws out a lot of the richness of wave interference between atoms. So if you believe that, then you would also maybe believe that this unwanted emission, so this 4 pi emission where you say you lose quantum information, maybe it's actually controllable. So in principle, this emission into 4 pi, as I argued before, is not really just independent. It depends on the positions of the atoms, maybe on the atom number. And then when we talk about quantum mechanics, maybe on the quantum correlations between the atoms themselves. So maybe one thing that you can do is if it's controllable, like so in an atomic gas, indeed the atoms might be kind of randomly moving around without your control. But maybe I can just start moving the atoms around by hand in a different system. So it's easy to do that in PowerPoint, right? I can just move these circles around. To do that in a real experiment is a bit tougher. But maybe Antoine will say we'll talk about at least one possible way to order atoms in the arrangements that you want. So one thing that I can do is I can try to move the atoms around until I achieve a perfect ordered lattice. For example, just a single 2D layer of atoms in an array. And it turns out, and this is something that again I'll describe later, if you redo this calculation, so you really send in a focused Gaussian field, and you look at the total field, you see that there's really not any emission into random directions anymore. So first of all, the light is coming in. You see no light transmitted. It seems like you see kind of 100% of the light reflected, and again, no light being scattered into random directions. So that's a kind of famous example that's emerged in the past few years about the power of interference and of spatial ordering. So if you do the calculation more carefully, what you find is that this kind of emission into 4 pi actually becomes suppressed with atom number. So it's not an independent quantity, but it decreases with atom number, like 1 over n squared. And so it kind of leads to an interesting possibility. Again, if you believe that the fidelity of quantum applications depends on this branching ratio, what's the probability that light goes into a good direction versus bad? Now you find that this ratio, because of this kind of suppression of emission into 4 pi, this ratio can actually be much larger than the optical depth d. And in particular, it can grow super linearly with the number of atoms. So I haven't proven that the system is useful for any quantum applications yet, but it's very suggestive that maybe we can use systems like these to essentially create a lossless, error-free atom-light interface. Just to maybe put in more specific parameters, if I take a 10 by 10 array of atoms with some subwavelength lattice constant, if I calculate this branching ratio of light emission, I would get something like 1,000. Okay, so 99.9% of the light in principle goes into the mode I want. But if I just naively apply the Maxwell block equations to the same system, recall in the Maxwell block equations, the spatial order has no bearing on the answer, I would get a branching ratio of just 1. Okay, so these are very, very different predictions. Okay, so the goals of these lectures going forward, more broadly, will be, on one hand, to develop a more fundamental theory of quantum atom-light interactions that really includes the atomic granularity and interference. And then we want to understand what are the implications. So, for example, if you're more interested in kind of applications of atom-light interfaces, for example, in the quantum domain, you might want to develop concrete protocols for applications, like a quantum memory, and prove a new error bound. Okay, so how much better can we do compared to what the papers told us? You can also imagine that anytime you develop an alternative or more fundamental theory, you might uncover surprising fundamental phenomena that you couldn't really recover just on basic principle from previous approaches. So going forward, I'll try to give examples of both of these, fundamental and application. Okay, so to develop an alternative theory, we should go back to this kind of illustration of the complexity of the full problem. So again, if I want to develop an exact microscopic theory, there's no ambiguity in what I have to do, but the difficulty is I just have to account for all these degrees of freedom, okay, which doesn't sound very practical or fun, right? So if interference and atomic granularity really matter to account for interference, it seems like I have to keep the atomic position, so I can't just naively smooth out the density anymore. Okay, so if I want to reduce the complexity, I have to look somewhere else. And it sounds kind of counterintuitive, but then the place that you can potentially reduce complexity is in this continuum of field modes, this infinite set of degrees of freedom associated with light. And it's counterintuitive because, recall, my interest in the first place is I want to talk about how light comes in, how atoms affect that light, and how the light, and what's the property of the light that comes out. And I'm kind of telling you that the way to do that is to throw out the light from the very beginning. Okay? So that sounds kind of strange, but I'll hopefully convince you that that's a feasible approach. So to understand that, how we can effectively throw out the light, let me just start with a kind of classical example of a microscopic theory of light particle or light atom interactions. And so classically, there's a kind of very similar problem. And so the general setup is something like this. Imagine I have some kind of point-like particles which are polarizable, which means if I apply an electric field or oscillating field, I can induce some oscillating dipole moment. So I'll apply that field by sending in some incident field, which I presumably know. Could be a Gaussian beam, for example. And then generally I'd be interested in what's the electric field at some other point, some detection point of interest. So to talk about the field, formally I can always write the total field as a coherent sum of an incident field and the field rescattered by these dipoles. So the scatter field will depend on the amplitude of each individual dipole times the Green's function, which basically propagates the field from the dipole location out to my detection point of interest. So electromagnetic Green's function sounds like a fancy word, but it really does nothing more than encode the kind of famous radiation pattern of an oscillating dipole. Okay? So one thing, just for kind of as a technical note, you'll notice that the electric field is a vector. The polarization, or the dipole moment, is also a vector. So this Green's function actually has to be a 3 by 3 matrix. So when I multiply this matrix by vector, I get another vector, which is the electric field. So here's formally what the equation for the Green's function, electromagnetic Green's function in free space, looks like. If it doesn't look familiar to you, don't worry about it. It's not something that I remember by heart anyway. I had to look it up. But again, the main point is that it's nothing more than the kind of a radiation pattern of an oscillating dipole. So for example, if I set the dipole to be oriented along z, then g alpha of z gives me the 3 field components of this field that I see here in space. Okay. And also importantly for later discussions, this Green's function has 2 very distinct types of terms. One is that you see there's a term that goes like kind of 1 over distance. That's the famous far field lobe radiation pattern of a dipole. But it also contains kind of electro or quasi-static terms that go like 1 over r cubed. So this is the near field associated with a dipole. So I can formally write down the solution for the field in terms of the dipole moments, but we don't actually know yet what are the dipole moments themselves. So to solve for the dipole amplitudes, I can simply say that the amplitude of dipole J is the polarizability of that dipole, which I presume I know, times the electric field. But this electric field is the total electric field. Okay? So it's the sum of the field that I send in, plus the field coming from all the other dipoles. So now you see that this basically just looks like a giant matrix equation that I can invert. So for example, I can define a giant vector P, which is just the dipole moments of all the individual particles or atoms. I can define a large vector, which is just the incident field value at all the particular positions of these dipoles. And then formally I can say that P is the inverse of this matrix, the identity minus the Green's function, times this electric field vector. Okay, so this is formally how you solve for multiple scattering in a classical disordered system. Okay? And in particular, it really includes interference and multiple scattering to all orders. It's the exact solution. Okay, so that's classical, and now let's talk about how we might come up with a quantum theory. So here I've just rewritten again this kind of total field as the sum of input and rescattered. And it turns out if you want to develop a quantum theory, it's pretty simple. You just put operator hats on all these things. And in particular, what that means is, when we talk about a quantum field, the quantumness is really contained in the sources, right? So these fields or these atomic sources might have noise, they might have correlations or entanglement, but the quantumness is not contained in the propagation. Okay, so this Green's function here is still the classical Green's function. That just simply says that whether you have a photon or a classical field, they both obey the same Maxwell's equations for propagation. Okay, so now in quantum mechanics, eventually I'll be interested in dynamics, calculating correlations in time. So whereas this equation here is in the frequency domain. So to go to time, I can just do a Fourier transform. And the complexity is really contained in this scattered field here. So I have some frequency dependence of the dipole moment. I have some frequency dependence of the Green's function and frequency dependence here. So when I Fourier transform, generally this will become a convolution in the time domain. Physically, that encodes just the delay of light propagation as you go from one point to another. So now here comes the big trick that's a little bit specific to atomic media. So an atom is actually, from the standpoint of its response to light, it's a very dispersive, very high Q resonant element. In particular, a typical resonance frequency of an atomic transition will be hundreds of terahertz. But the spontaneous emission rate, or the line width of an atom, so this is the bandwidth around which an atom will really talk to light efficiently, that's really just given by a few megahertz. So anytime you have very, very high Q elements, it means that when you send light through such a system, you'll get a ton of dispersion and delay of your pulse. And nearly all of that will be attributable to the atoms themselves, or the resonant elements themselves, rather than empty space. Okay, so in other words, if you just take an atomic medium, you send a pulse of light, you'll see a huge delay. Even if you set the speed of light to infinity, you'll see exactly the same delay. It's all coming from the atoms. What that means in practice at a mathematical level is that this kind of dipole moment here has a ton of frequency dependence. It varies strongly over a bandwidth of a few megahertz. But in free space, if you kind of change your frequency of light by a few megahertz, you don't really notice that effect until you go to very long distances. So what that means is that you have to keep the frequency dependence of your dipoles, but the frequency dependence of your Green's function and here you can basically throw away. You can just replace it by, for example, the resonant frequency of the atom itself. And now, since you only have frequency dependence in one term, when you do this Fourier transform, it becomes straightforward. You lose this convolution in time, and now you get this generalized input-output equation in time for the atoms. So now I've really generalized from our kind of abstract dipoles to two-level atoms. And notice that I have operators here. So basically my quantum field operator, my total field, is a sum of the incident field that I send in, plus the rescatter field, which depends on the atomic lowering or atomic coherence. And in particular, I see that now I've really lost the field as an independent degree of freedom. If I want to calculate the total field or its correlations at any point in time and space, I can do that just by knowing the correlations of the field that I send in, which presumably I know, and the correlations of the atoms. Okay, so I've gotten rid of this infinite Hilbert space a priori that's associated with the light. So again, just like in the classical case, I have a formal expression for the total fields, but I don't know what the sources are yet, or I don't know what the atoms are doing yet. I have to solve for that. So if I imagine going back to the full system of atoms and light, I can formally write down Heisenberg equations of motion for the atoms. The atoms will naturally, just like in the classical case, be driven by the total field. But you saw in the previous slide that I can re-express the total field just in terms of other atoms alone. So basically I get equations where the evolution of one atom just depends on the incident field and on other atoms. So I can find some equivalent effective Hamiltonian from which I can derive those equations of motion. So I have an effective Hamiltonian now that depends on the input field that I send in. And this really describes the effect of multiple scattering between atoms. So this kind of form here, if I just kind of draw it out, it basically says that if I have an atom J, which is excited, that atom can go from the excited state to the ground state, and another atom I can go from the ground state to the excited state. That's kind of intuitively what you expect from photon emission and reabsorption. Okay? And furthermore, the amplitude of that kind of scattering process will depend on the Green's function, so it depends on how the light propagates from atom J to atom I. So even though I presume you haven't seen a Hamiltonian like this before, the form of it is quite intuitive. Okay? So there's one kind of technicality here, which you shouldn't worry about too much, but for the kind of more theory-oriented people in the audience, this is actually a non-Hermitian Hamiltonian. So this Green's function is complex symmetric as opposed to Hermitian. So the fact that it's non-Hermitian just simply says that your system is open, it can decay. So if you have excited atoms, eventually you can spontaneously emit into 4 pi out to infinity. So a non-Hermitian Hamiltonian is not a complete description of an open quantum system. A complete description, you have to go to something like a density matrix or master equation approach. So I've written down the full master equation for this effective Hamiltonian here. Again, I don't expect you to remember it. I just write it down for completeness. And I guess the spirit is anytime you want to calculate a real observable, like what will you see in lab, you do have to somehow revert to a master equation or some equivalent form. But it turns out to understand a lot of the physics, just the intuition, you can work just with this kind of effective Hamiltonian and look, for example, at the properties of its eigenstates. So I'll focus more on that kind of simpler approach here. But again, keep in mind, if anytime I present observables, it does involve this kind of more complex master equation down here. Okay, so let's just kind of take this, this so-called quantum spin Hamiltonian, quantum spin model, and take a very simple example of a single undriven atom. So here's the effective Hamiltonian in general. And if I just have one atom, I get rid of these indices I and j. So I and j are both equal to 1. So I have the Green's function of this one single atom at its own location. And now I have the product of sigma Eg times sigma Ge. So that's the product of an atomic raising operator and an atomic lowering operator. That's nothing more than the excited state population itself, so sigma EE. This Green's function of in free space at its own location, I can readily evaluate that from the formula I presented a few slides back. That just turns out to be I over 3 times the wavelength of the light. And now when I multiply everything together, I get a very simple effective Hamiltonian describing this one undriven atom. So it's a Hamiltonian that depends on the excited state population. You said that the excited state population acquires an imaginary frequency. That, of course, corresponds to the spontaneous emission rate of the excited state. So even though this looks like a kind of unfamiliar, strange form to most of you, it just encodes basic physics that you know about and maybe from other contexts or derived in other ways. It just says that a single atom spontaneously emits at a rate gamma naught. So I guess the point of this illustration on one hand is to show that even though it seems kind of abstract or unusual, if you really just start to play with it, it doesn't, in simple cases, it just encodes the physics that you probably already know. More generally, for many atoms, so if I go back to this form, the main point that you can already take away here is that this Hamiltonian generally depends on the product between atoms I and j. So I can't factorize it into this kind of summation of individual atoms anymore. So this kind of factorization here is essentially what goes into the Maxwell block equations. I assume by hand that my dissipation or my spontaneous emission between different atoms is independent. Whereas this equation here really encodes that this emission is correlated, and therefore it encodes the effects of wave interference. Okay, so now I've introduced an alternative theory to capture quantum atom-light interactions that in principle includes wave interference and in a non-perturbative way. So just to recap, we have this kind of open system or effective Hamiltonian that describes how atoms interact with each other through the effect of photon absorption and re-emission, or multiple scattering. And then in this formulation, I've gotten rid of the field as a real degree of freedom. So basically the way this works is, if I have some simple system of a few atoms, I could just plug this Hamiltonian into a computer. I could solve for the entire wave function as a function of time. And once I have that wave function, I can calculate any correlation function between the atoms that I want. So once I can do that, now if I want to find a property of the field at some point in space, I can just simply re-express that correlation function of the field in terms of correlation functions of the atoms. I evaluate those using this full Schrodinger wave function, and then I recover any property of light that I'm interested in. So that's a kind of general recipe of how one might use these equations. So nothing I said, these equations are actually not new. They have a long history in many different reincarnations. But despite the fact that they're not new, I think they've just been kind of largely ignored as a kind of practical possibility of a quantum theory. And that, again, it goes back to the fact that the Hilbert space, it goes like 2 to the n. And that's not really, and depends on the atomic positions. And that, a priori doesn't seem very practical when you have many atoms. So the challenge going forward is to, try and, of course, right, in general, maybe these equations are hard. But maybe it's not completely hopeless. Okay? So maybe we can find limiting regimes that are both interesting and useful. We can gain interesting intuition from them. And maybe we can make good approximations depending on the regimes that we're interested in. And maybe have then build up some effective theories going forward. But again, which include interference fundamentally in the phenomena that come out. Any questions on this part? Okay. So admittedly, this Hamiltonian is a little bit abstract, and I think the simplest way to get intuition is just to try it out. Let's take some simple physical example. Let's stick it into a computer and see what comes out. So again, here's the kind of spin model in general. And to start making the problem a little bit simpler, we have to specify the geometry of atoms. Let's just take a 1D chain of atoms. So it's an ordered lattice with some well-defined lattice constant d. So it's n atoms. So it's a 1D chain, but it lives in 3-dimensional space. In other words, it really does talk to the 3-dimensional continuum of electromagnetic field modes. So this Hilbert space still grows like 2 to the n in general. But maybe let's take a simple limit where let's just say there's at most 1 excitation in the system. So now my Hilbert space is just n in size. So for example, the first atom can be excited, or the second one, or the third one. And then within this subspace of 1 excitation, now it becomes efficient. My Hamiltonian is really just an n by n matrix, where the matrix elements between excitations I and j are just the classical Green's function itself. Okay, so it's really just, if I say Rj is this point of the dipole, I have to find the dipole radiation pattern at this point Ri. And therefore I can build up, just numerically this n by n matrix. So just a bit of an aside. So within this single excitation space, an arbitrary wave function will look something like this. So any atom j can be excited with some amplitude Cj. The dynamics of this system will just be given by the Schrodinger equation. So Cj dot is minus IH times the wave function. And once I project back into these individual amplitudes, the dynamics of Cj will just depend on the product of other amplitudes of atoms Ck being excited times this Green's function. So alternatively, I can consider, so here I kind of created what looks more like a kind of quantum formalism to describe the system. But I could consider just some alternative system. What if I have just a system of classical radiating dipoles? So I have dipole amplitudes Pj, which can be driven by the fields generated by other dipoles. So it turns out that the equations of motion for this classical system look exactly like that of the single excitation amplitudes in the quantum wave function. That's just to say that all of this physics of a single excitation has a classical linear optical interpretation. So I'll be using kind of wave functions and the Schrodinger equation just to provide some uniformity, and that's what I'm more used to. But as long as I talk about single excitations, I want to emphasize that all the physics that comes out, and this will be important later, all that physics I can in principle learn about and read about in a classical optics textbook. Okay, so if I can build my Hamiltonian in a computer, I can numerically diagonalize that. If I have n atoms, I'll have n eigenstates, which I'll label alpha, going from 1 to n. And generally, it'll be a superposition of different atoms excited. So any given eigenstate alpha will be of this form. I can just numerically take any one of these eigenstates randomly. I can plot what are the individual amplitudes for atoms j to be excited, and I'll get some pattern. Okay, so I guess this is just to say that an eigenstate will not just be a product state of one individual atom excited. And that's due to this kind of photon interactions between all the atoms. So these eigenstates will also have complex eigenvalues, and they reveal two different things. So the real part of this eigenvalue physically represents some kind of frequency shift of this resonance, of this collective mode, away from the bare atomic frequency. So this, you can think about some dressing of atomic excited states due to the fields coming from all the other atoms. At the same time, these eigenvalues will have an imaginary part, which reflects an enhanced or suppressed decay rate of this collective state, physically due to interference, and in general will be different from the single atom spontaneous emission rate, gamma naught. So if I just plug it into a computer, I can build up a graph or a plot like the following. So what I can imagine is I can fix the atom number, like n equals 30, and I can just begin with one fixed value of the lattice constant. For example, d is 2.1 times the wavelength. So I build up the Hamiltonian. I calculate 30 eigenvalues. And here I'm going to plot the real parts of these eigenvalues. So these are the frequency shifts of the 30 eigenmodes of the system. So there's 30 dots along this vertical line at a fixed distance. And so you see there's kind of 30 different points, but in terms of the value, they're all centered around 0. So basically when the atoms are far apart, in this case it means kind of a few wavelengths. These kind of effects of interference don't seem very prominent. These 30 collective modes all have a resonance frequency that's close to the bare resonance frequency of a single atom. So I can do that for one distance. I can change the lattice constant, do another calculation. That gives me another vertical cut, and so on. I can also do the same kind of plot, but now for the imaginary part of the eigenvalue, or the decay rate. Again, for a fixed value of the lattice constant, I get 30 different values. But you see that they're all centered around 1. So basically, these collective decay rates are all pretty similar to the emission rate of a single isolated atom. So now I can repeat the calculation, but make the lattice constant smaller and smaller. So you see that now, as the atoms get closer, the atoms start to notice the effects of interference and multiple scattering a little bit more, and even more. And what's interesting is when I bring the atomic lattice constant below lambda over 2, you notice a very different qualitative behavior emerge. So you see that in these kind of collective modes, there's a subset of them that have a very small decay rate. It seems like the decay rate is nearly 0. So these are highly, quote, subradiant states in atomic physics or quantum optics language. So you can ask, what does close to 0 mean? So I can take the same plot. I can replot it on a logarithmic scale. And you see that kind of for 30 atoms, I can have a 1,000-fold suppression of the spontaneous emission rate compared to that of a single atom. If you do a more careful numerical analysis, you see that the smallest decay rates of these systems, so for the lowest few modes, it goes something like alpha squared, where alpha is just the index of the eigenstate, 1, 2, 3, and so on. But it decreases like the number of atoms in the system, like 1 over n cubed. So as you build longer and longer chains, you very quickly develop a set of modes where the decay rate is effectively 0. So what this is that the interference of wave emission really matters at close distances. You get a completely different answer compared to the Maxwell Bloch equations, and the atoms are not at all independent objects in terms of how they emit light. Okay, so this is just the numerics, and now we can try and develop a bit of intuition of where this kind of subradiance comes from. So it turns out a good place to develop intuition is just to go to the infinite system limit, but still with just one excitation. And the nice thing about going to the infinite system is, a priori that might sound like an infinite Hilbert space, but because of the periodicity of the system, I know that Bloch's theorem has to be enforced. So without doing any work at all, I can automatically tell you that every single excitation eigenstate will look of this form. So one atom J will be excited with a relative phase e to the I kz, and this k is just the Bloch wave vector of this particular mode. So once I have Bloch's theorem, the next thing to do is to try and plot a band structure of the system. So here I'll just kind of start with a kind of empty plot here. So because we have a non-Hermitian Hamiltonian, technically the eigenvalues, the Bloch eigenvalues can be complex. But just to make it look a little bit more like a standard band structure, for the moment I'll focus just on the real part of the frequency. So what are the resonance shifts away from the bare resonance frequency? So to plot a Bloch band structure, recall as well that in this kind of Bloch theory, this Bloch wave vector really only has to be uniquely defined within the first Brillouin zone. So from minus pi over the lattice constant to plus pi over the lattice constant. Okay. And here I just kind of noted for reference what's the bare resonance frequency of a single atom. So it turns out you can really, you could diagonalize H almost analytically, but actually it turns out without doing much work, you can have a very good argument about what this band structure should look like in general. So first of all, recall that my atoms are very highly resonant elements. They really only respond to light within kind of characteristic bandwidth given by gamma naught, the spontaneous emission rate. So because of that, now once they start to interact via light, I can kind of guess that the band, whatever details of the shape are, they'll have a very narrow bandwidth. So this band will be almost completely flat. They'll have a characteristic width of around gamma naught. So to get some more intuition, I can also draw in just the dispersion relation of light in empty space, omega equals ck. And the reason it's convenient to do that is the following. So here I've been using my spin model to just talk about the eigenstates of the atoms. But in principle, I could use this kind of input-output relation, or I can use this fact that the total fields can be reconstructed from my scattered field. And again, because of the periodicity of the system, it kind of makes sense that the electric field, or the fields that are generated, should also obey Bloch's theorem. So in particular, if I have a Bloch wave vector k that for this kind of atomic excitation, if I look at the electric fields associated with this mode along the chain, it should also have the same wave vector dependence e to the I kz. So here I'm kind of taking like a plane wave decomposition of the field associated with this atomic excitation. There's one detail though, which is that even though whereas the spin chain really just lives in a one-dimensional space, the electric field lives in a three-dimensional space. So this wave vector k is really just the kind of parallel component of the wave vector, and there should be a transverse component of the wave vector as well, which describes how the field looks like as you go away from the atomic chain. And Maxwell's equations imposes a distinct dispersion relation. So k squared plus k perpendicular squared has to equal omega over c squared. And now you see that drawing in this kind of dispersion relation, omega equals ck, is quite nice because it separates two very different kinds of solutions for these spin waves. In particular, in this region here, or in this region here, so-called beyond the light line, k itself, the parallel component, is already bigger than omega over c, which means to satisfy this dispersion relation, k perpendicular has to be imaginary. So in the transverse direction, it's really an evanescent field, or physically it describes what looks like a guided mode of light. So in conclusion, the light out here, these modes here are basically kind of the physical interpretation, is that the atomic excitation is just acting as a waveguide for light. Whereas here, these modes can talk to radiation modes. And so, again, without doing any serious work, I can already tell you what the imaginary part of these frequencies are. These modes here will be exactly lossless in the infinite system limit, whereas these modes here will still spontaneously emit into 4 pi. So now we've arrived at one of the main punchlines. When I have ordered chains of atoms, the physics of subradiance is exactly equivalent to the physics of classical optical waveguiding. For those of you who are a little bit familiar with nanophotonics, the physics I described is really completely analogous to what's known as a photonic crystal waveguide. So to have these kind of possibility of guided modes, the only condition is that you need some modes beyond the light line. So that will be fulfilled if your dispersion relation, omega equals ck, intersects the edge of the Brillouin zone above the bare atomic frequency omega e.g. So I can take that same condition, I can convert it back into distances, and that's completely equivalent to the lattice constant being smaller than lambda over 2. So we saw that that was kind of the magic threshold in the finite atom case. And so now we can finally understand why a finite chain has a small but non-zero decay rate that shrinks with the size of the system. Imagine I just start with a normal classical optical fiber. You know that thing in principle guides light perfectly without any loss. But if I cut the fiber at some point, now light can spray into free space and I can start to lose energy. So this finite atomic chain is exactly a cut fiber. So to kind of confirm that, you can take, for example, 30 atoms. You can numerically diagonalize to find the most subradiant state. I can reconstruct this total field using this kind of input-output relation. And you really see that it has an emission pattern that looks like a cut fiber. So maybe I'll just stop. This will be my last slide before I stop. So even though, so you see that once I create a subwavelength array, these subradiant modes naturally exist. They're guided modes of the system. But this also might give you a hint of why subradiance is so elusive to see in real experiments. So it's possible that subradiance is just always there. But by definition, these modes just kind of decouple from light. So when I say it's hard to see subradiant states, what I mean is that imagine I gave you this atomic array. You know there's subradiant modes there. And the way you normally kind of talk to these atoms is you shine in some laser field, right? And you see what the effect is. But a laser field by definition is a radiation field. So no matter what direction I come in, this laser field always lives inside the light cone, but the states of interest always live outside. Okay? So when I start the next lecture, I'll talk about some possible way to start to address these subradiant states and to use that as a resource in quantum applications. So with that, I'm done for this lecture, but I'm happy to take any questions that you have. Okay, sure.
I mean, yeah, so I think the value of D was around 0.04.
Oh,
So what determines the lowest value you get?
This is just a numerical calculation, so I can make the lattice constant as small as I want. So basically, to get this interesting subradiant behavior, you need a lattice constant below lambda over 2. Okay. But any value below lambda over 2 is, in principle, sufficient. Okay. So in practice, it's hard to get it's hard to create an atomic lattice in 1D that's below lambda over 2. There's some tricks you can play, but it's not completely straightforward experimentally. So next time I'll talk about one possible way you can do that by using some other dielectric materials to create a smaller lattice constant.
But there should be more limitations when you get much further in terms of atomic repulsions or.
Oh, okay. Right. So when you get really, really close, eventually, aside from, if I had the technology to just bring atoms as close as I want, eventually I would have the physics of just, chemistry would start to turn on. My notion of an atom now is it has kind of distinct orbitals like a ground state and excited state. If the atoms become too close, then these orbitals start to hybridize and I get chemistry. But that's a completely different scale of interaction. So, a typical wavelength of an atom can be something like a micron, but the typical wavelength where the distance where chemistry starts to turn on is like a nanometer.
say that however, the van der Waals interactions with dipole-dipole, they are included, right? Because they are light mediated. I mean, they're also in the green function in a sense, right?
Okay, yeah. So that's a good question. It has to deal with when you derive this Green's function-based Hamiltonian. So if you start from the full Hamiltonian of atoms and light, there are so-called rotating terms and non-rotating terms. So it's the non-rotating terms that give rise to these van der Waals or Casimir-Poulter interactions. And in this particular Hamiltonian that I wrote down here, I ignored those terms. But I could have added them in just by, I could redo the derivation with these non-rotating terms. And then
they are not in the 1 over rho cube terms.
Okay, so it depends on what you, So it has the van der Waals interaction between the excited state and the ground state. So that's included. That's effective of the rotating terms. But if I want just the ground state interaction, the chemistry part, I would have to include the non-rotating terms.
Maybe one last question. In this class, actually,
Mm-hmm.
even when you're below 0.5, you have a lot of the other way. Most are not gradient.
Right.
So when you're having your main structure approach, and they were also gradient, right?
No, sorry. So so in general, your block wave vector can go from minus pi over d to pi over d, and it's only these modes here. So so when k is bigger than omega over c, so these modes in this triangle and this triangle, those are the subradiant ones. And the remainder of the modes here are the radiant ones. So now when you go to a finite size system, you essentially get that same fraction. So this fraction of modes would have a non-zero decay rate. This fraction of modes would see a decay rate that goes to 0. So you can never just completely hide your atoms from light. There will always be some modes that are able to radiate into some direction.
Is there some kind of, some rule that, in the end, so you get some subradiant state, of course, but you also have superradiant state. So is there some kind of rule that in the end the sum?
Yeah. So exactly. Yeah. So the sum of the decay rates, you can calculate that from taking the trace of this Green's function, and it has to come out to n times gamma naught.
Right. So there it is.
Yeah.
Okay. So thanks, Darek, for this lecture. We will make a 15-minute break and come back in 10 minutes and for the next lectures. Please exit the door in the back. Thank you. Just one quick announcement. Maybe the lectures are live. So if someone from an institute or university wanted to come and was not able to come, you can forward them the link. I send you the link.